In this video, we're going to learn about the 4 types of radiation, and then we'll see how we can complete nuclear equations, which sounds hard, but I think you'll be pleasantly surprised. So on this slide are the 4 types of nuclear emission that we'll be talking about, with different types of radiation. We have alpha particles, the beta particles, positron, and gamma. Now I'll be giving you the first 2 columns on this table, so I'll give you a list of the radiations along with their symbols, so you don't need to worry about memorizing that. The first 3 are actual particles, and so they have symbols that have numbers with them. This right here is what's going to be useful for us and what we're going to be trying to do. And then gamma ray is just a form of energy. So it's not a particle, and so you notice here they use the Greek letter, the lowercase gamma, and it doesn't have any numbers because the numbers would all be 0 because it's just energy, it's not a particle. Now just a few tidbits about each of the types of radiation. Alpha, the first one, out of the 4, this is the largest and the slowest moving relative to other radiations. You can see it has a plus charge of 2. It's actually similar to a helium nucleus is what we might imagine. But it has a positive charge of 2, and it's a large, slow molecule, so it has low penetration. Your skin would stop it. It doesn't really penetrate. It is very large, however, so if it comes in contact with certain kinds of tissue and things, it can be very damaging because of its size. Now then we also have we have the beta, which you see it has a -1 charge. The beta is much smaller and it's faster. This is like electrons from the nucleus. Now when I first heard that, I thought, what? Because electrons are outside the nucleus in the electron cloud. Well, these are not electrons that are just in the nucleus. In this transformation, and remember what's happening is radioactive isotopes are unstable. So their nucleus is undergoing transformation to try to be stable. So in this case, a neutron actually changes into a proton. And in that process, an electron is emitted. So in this nuclear process, an electron is one of the byproducts, and so the electron comes out of the nucleus. So the electron's not just sitting there in the nucleus, it's not an electron we didn't know anything about, it's as a result of the changes in the nucleus. Now because these are smaller and faster, they actually can penetrate more than the alpha particles. So maybe something like a piece of paper would have to stop a beta particle. And then a positron, which would be similar in size, but instead of being negative charge like an electron, it's a positive charge. And this is the result of when the protons transform into neutrons. So it's the opposite. Again, so this is all happening within the nucleus, and then this radiation is emitted out of the nucleus. Now, gamma rays, they are so much energy, so they're not particles, but they have a really high penetration. So it takes like a thick piece of lead to stop the penetration of gamma rays. So people who work with radioactivity, they have to consider their PPE very carefully based on the type of radiation and how it penetrates. So this gammas take lead. All right, so what we're going to do is learn how to write a nuclear equation. We are going to be referring back to the symbols. They'll tell us what particle we're using. In fact, they tell us a lot. So first, let's just understand a little bit about nuclear reactions and what we're going to use to write them. So a nuclear reaction is like a chemical equation, except it's showing us a radioactive decay. So it's showing us what's going on in the nucleus and how it's transmutating or changing into a new isotope. So we saw one in the first video and what they look like. They use isotope symbols and things. Now, the thing that we're going to use to help us get our answers is right here. So we're still going to be calling the reactants are going to be on the left and the products are going to be on the right. So that's still the same. Oh, the arrow. Sorry, I didn't say arrow. So that's still the same. But how we balance it and figure out what's missing is what we know is that if you add up all the mass numbers on the reactant side, that has to equal the sum of the mass numbers on the product side. And then likewise, looking at the atomic numbers, if we add all the atomic numbers together on the reactant side, that will equal the sum of all of the atomic numbers on the product side. Now, at first, just me telling you this in words, it might seem confusing. In fact, it probably does. But let's see what this means in an actual example. So again, keep in mind, our goal is going to be to make the sum of the mass numbers the same on both the reactant and the product side, and the sum of the atomic numbers the same on the reactant and the product side. So here's an example equation, and we are going to think of it, this is the reactants. It only has the potassium 40 here, and then we are going to have an arrow, which is right here, and then we have the products. Now they are giving us all of the information about the reaction except this one little question mark. And that's what we're going to use. I'll make it darker. That we're going to use the balancing to figure out that question mark. We want to know the question mark is. Okay, so let's start with the mass numbers. So I see on this side I have the number 40, and there's only one, so I don't add anything up. Here I have a question mark. I'm just going to say X because I don't know it. I'm adding it to a 0, and then gamma has zeros too. Here's the 0 I'm looking at. Gamma has 0 too, so I don't have to say anything. So what number plus 0 equals 40? Okay, let's put in the number 40. So that's going to be the mass number of my new isotope, is 40. Then I do the same thing with the denominator. So here I just have 1, so this is 19. There's the arrow. Now it's a question mark. I'm going to say Y just because it will be a different number than the one above. And I'm adding it to a -1. So adding a -1 is like subtracting 1. So I think to myself, what minus 1 equals 19? And the number would be 20. So 20 minus 1 equals 19 because both sides have to be the same. So this number is a 20. Now let me go to I need to know what element. I put a periodic table here. I've got to go through my slides. Here we go. And element number 20 right here is circled. It's calcium. So that means the symbol is going to be calcium. So that is what goes in the question mark. Now I'll rewrite the whole equation. So it would be 40 over 19K, arrow, and then the question mark is 40 over 20 Ca plus the beta particle, that's the symbol, plus the gamma. Now if you look, this side is 40, this is 40 plus 0, so that equals 40. This side is 19, this is 20 minus 1, which is 19. So this is the correct equation once it's completed. Oops, I don't want to use that. So now that you get the general idea, let's try some specific types of emission. So this is alpha emission. So this is the decay, which is really just another word for like the nuclear reaction, the decay of the nucleus by emitting. And when something is emitted, it's going to be on the product side because it's released. So it's going to be on the right-hand side. And this is an alpha particle. And from our previous slide, alpha has a symbol 4,2He. So that's what we're going to use for alpha. So the question says, write a balanced nuclear equation to show how americium-241 decays to form an alpha particle. All right. So I know the top number is 241. Now, americium, I don't know its atomic number. Let's go look. Now, it's going to be at the bottom. Here it is. Am. And sometimes we're going to have elements that are down here in the inner transition metal. So, in the inner transition metals. So you might have to search around a little because they're not ones that we're used to looking at. So the symbol's Am and it's element 95. So it's Am 95. Okay, so what I just did is I just wrote that. Now it decays, that means that's our reaction, to form an alpha particle. Okay, so alpha particle is 4,2He. Now we know there must be a new isotope form, right? Because this is not balanced. So I'm going to write it above it just to try to help you. This side has 241. This side only has 4 plus some unknown element. So let's see, what would that have to be? 237? 237, right? So we'll put the 237 here because 237 plus 4 is 241. Okay, and then let's do on the bottom. The bottom is 95 on this side, the reactant side. This is 2 plus some number. So this would have to be 93, right? Because 93 plus 2 equals 95. Now, I don't know what element it is. I have to go back to my periodic table and look for element 93. And element 93 is right here, neptunium, Np. One more. Okay, so then I will write Np. And so the answer, even though I have different colors, this right here is the balanced nuclear equation for the how americium-241 decays to form an alpha particle, and we figured out neptunium-237. All right, so alpha particles, this is what it would look like. And it doesn't matter on the product side. If I would have written neptunium before the alpha particle, that would have been okay as well. I always just write down what they give me. All right, so let's try a beta particle. So the decay of a nucleus by emitting a beta particle. And a beta particle has a symbol of 0, -1, That's the one we want to use. So it says, write a balanced nuclear equation for the beta emission of iodine-131. Iodine-131 is used as a very successful therapy for thyroid cancer. So let's see, iodine. I need to know its atomic number. I got to go to the periodic table. So iodine right here is 53. So what I've written so far is just this. Now it says it's a beta emission, so there's my iodine, and it's going to release a beta. So that's the symbol for beta, so now I have that. And then it's going to be some other element that I don't know. I've got to figure out. So on this top it has 131. This is 0 plus some unknown number, but this number has to be 131 because 131 plus 0 equals 131. So I'm going to put 131 here. Then I go to the bottom number. This number is 53. On this side, there's a -1 plus some number, so it's like subtracting 1. So this would be 54, right? 54 plus a -1, or 54 minus 1 is 53. So this is 54. Now I'm going to go to the periodic table to figure out which one it is. 54, xenon, right next to it, which makes sense. So it's xenon. And so the answer for the balanced nuclear equation for a beta emission of iodine 131 is right there. So iodine emits a beta particle, and now you have xenon formed. So let's try a positron. Hopefully you're seeing a pattern here now. They all kind of work the same way. You do need to take time, read the problem so you're not messing up numbers. So a positron, the decay of a nucleus using a positron. So the symbol that we're going to use for a positron is 0 plus 1, E. So write a balanced nuclear equation for the positron emission of arsenic, which is As74. So the 74 goes up here. So I've got to go look at my periodic table and find arsenic right there. So it's element number 33. Now it is emitting, so what I just did was wrote that. And it's emitting a positron, so let's put the positron symbol in. And there has to be something else, right? Because it's definitely not balanced. So on this side I have 74. It's going to a 0, so whatever this number is has to be 74, because 74 plus 0 is 74. Has to equal the same on both sides. Down here I have 33. This is a plus 1, and then it's plus some other number. So this would be 32, right? Because 32 plus 1 is 33. Now to figure out the element, I'd go to my periodic table, and here's 32, so it's germanium. And so the answer to this question, the balanced nuclear equation, is this right here. So now let's look at gamma. So the first three are all particles, so they all have symbols. So we have alpha, beta, alpha, beta, positron. And now let's look at gamma. So gamma, which doesn't have a symbol, you just use the lowercase Greek letter gamma. This is energy only. So there's what we call no transmutation. Another way to say that is the atoms won't change, because this is just energy, it's not a particle. Now, it's not uncommon, so this is the equation here is technetium, the Tc. This little m means metastable. Sometimes instead of m, they'll just use a little asterisk. And what it's telling you is that one has too much energy. So then what you'll notice in the product side, there's no longer an M, and that's because the energy is released as a gamma ray. Now, evidently, this technetium remains radioactive, but it no longer has that extra energy, so it must emit other forms of radiation. But technetium is something they use in heart tests when they're looking at heart imaging. All right, so it's not an incorrect thing. It's not a coincidence that both sides have technetium-99, because all that's happening is it's starting with too much energy, metastable, and then it's releasing its energy as a gamma ray and just becoming technetium-99. All right, so I have more videos, and some of them are probably these exact examples, but you can see if I said something a little bit differently if you want, or just review these if you're having trouble. Also, I just welcome, if you're struggling with one, for you to send me an email, and I'll help. Let's see why you're not getting the right answer. All right?